Hello. So we have the pleasure to have Desiree instructors who will be presenting the Anton 2 enhanced sampling capabilities. So let me introduce Abby Robinson-Mosher, who will be giving the talk. And also from Desiree, we have Ken Mackenzie and Michael Levine. So thank you for the opportunity to listen to the talk.
And thank you for having us, and thank you for the introduction.
Sure. How do you want to handle questions? We can answer through chat, collect the questions, or?
So I'm pretty flexible. If people want to, if you wanted to ask people, so if people want to ask questions in chat and they seem like they come up at a reasonable time, if you wanted to then convey them while we're going, that would be fine with me. Or if people want to hold questions to the end, that's also fine.
Okay.
As I go through the slides, it's possible Michael will also chime in with stuff if I miss something or if there's something that's a good perspective. But yes, I think people should feel free to ask their questions in chat, and then if you could raise them. So thank you all for coming. I'm going to talk a little bit about the enhanced sampling features that are available on Anton 2. Let's see. So the enhanced sampling on Anton 2 is driven under the hood by something called TSS, which is short for time square sampling. And this is an enhanced sampling approach that is sort of qualitatively similar to simulated tempering or simulated Hamiltonian tempering, which itself is sort of like a sequential form of replica exchange molecular dynamics, which people may be more familiar with. In replica exchange molecular dynamics, you have a whole bunch of different Hamiltonians, say temperature Hamiltonians, and you're doing separate simulations at each one in parallel. And then periodically, you can swap simulations between different Hamiltonians, which lets you exchange states sort of up and down the temperature scale. Simulated tempering is kind of like doing that, except you run a single simulation, but periodically change which Hamiltonian it is being simulated with. So you move to a different temperature. To do this sort of correctly, you have to have estimates of the weights for the different Hamiltonians. And those are sort of free energy based weights. So that's often something that can be a little tricky in setting up simulated tempering. And you maybe have to like estimate them a priori or run for a bit, estimate them, restart. Happily, TSS actually has built-in online free energy estimators. So you don't have to come up with a priori estimates of your Hamiltonian free energies to do this. You can just run it and we'll figure that out for you as it goes. And the reason we developed an approach like this for Anton is more well-suited to single long simulations than to lots of short parallel ones with communication. So this is particularly well-suited to the kinds of runs you might be doing on Anton at PSC. In terms of time square sampling itself, if you're interested in learning more about the method, the paper is finally out on arXiv, which there's a arXiv link in the bottom left here. And the code for TSS itself, independent of the Anton code, is available on GitHub with some illustrative things if you want to look at it, but that won't be directly relevant to what you might be doing at PSC. Okay, so to talk a little bit about how this might be of interest to the kinds of things you might be wanting to run here, let's say you've got a system that is sort of coarsely described by this free energy landscape in the bottom left, where you got the little guy walking around in the low free energy well down there. And you might be interested in exploring both of these metastable states, but you've got a high energy barrier between them. And if you're running at sort of your physical temperature of interest, you're not easily going to cross the barrier and explore the other state. You may do it after running for a long time, but it's going to be very hard to get a simulation which has a correct balance between the two states. So if you can have your simulations explore a higher temperature T2, where the effective barrier between the two states is lower, then you get some equilibration between the two. And then if you relax back down to the lower temperature, at least some of the time you will show up in the higher free energy state on the other side of the barrier. When you use TSS to do this, or if you use well set up simulated tempering, you will get the correct balance of occupancies between the higher and lower wells, which is sort of the nice thing about using these enhanced sampling approaches. And more generally, you will explore, ideally, all of the metastable states that might be relevant. Michael, am I forgetting anything important here?
No, I would stress that you can do this with any number of states. So here there's 2, but no matter how complex the free energy landscape is, this approach will work and you'll eventually get the right relative occupancy of all the states. So you don't need to know anything about the states beforehand when you do this with, say, temperature. But I think Avi will talk about other things that you can modify about the Hamiltonian, which maybe you can use the information about the states for that, but you don't need to know anything about how many states there are or how big the barriers are when you start doing this approach. And it'll kind of, part of the built-in online estimators will help figure out the best way to do this for your system as it goes.
Yep, that is very true. It looks like there may be a question in the chat.
Yeah, the question is this simulated annealing?
It is not simulated annealing, which I believe is a approach for like finding the lowest energy state. Simulated tempering has some, it looks a little bit like simulated annealing, but it's not quite the same thing. But you can use it to achieve some of the same outcomes. Simulated annealing, I think, will tend to find you the lowest free energy state. Simulated tempering will get you the correct distribution of occupancies of low free energy, of free energy wells, while not only finding you the lowest one. So, okay. This is talking a little bit about the simulated tempering applications that are available. There is also something called tempered binding that has been developed at DesRes, and there's a paper on this in PNAS from 2019. What tempered binding is about is, let's say you're looking at association between two proteins, or you're looking at protein ligand binding. If you just run conventional MD and let them come together, it's not uncommon for them to get stuck in some metastable state that isn't the low free energy one, or just get stuck and not explore a lot of the states that you'd like to see just because of the barriers or the kinetic traps that keep you there. So what this illustration is showing you, each of these dotted lines is essentially conceptually an interaction between the two proteins. And you can use the tempering approach to explore different strengths of those interactions that will let you do some of the simulation where the interactions are fully on and will let you have the correct physical interactions between them so you can explore a given metastable state. But then you can also weaken them, which lets it leave that metastable state, maybe move away, maybe sort of reorient, and then find other metastable states that would be of interest rather than getting stuck in the way you might in a conventional straight up simulation with your normal physical properties. This here is an illustration of what that looks like in a tempered binding run. And it's basically jumping around these different lambda rungs. Each lambda corresponds essentially to a scaling of one of those interactions. And it's saying, you're going to spend some time at the bottom here where you're in essentially the normal interaction physics. You're going to move around a bunch. You get to dissociate, move around, reorient, and then come back together. Something that you could be concerned about is that you don't spend a lot of time in the Hamiltonian that's the one of direct interest to you, the physical one. But if you have correctly estimated free energies for each of these lambda rungs, you can actually use states that weren't simulated in the physical rung and reweight them to get their contribution in that rung for looking at like the relative abundances of the different metastable states. And happily, TSS will generate those free energies for you so you can use them to do the reweighting. And I think that can be done partially with a tool that's available at PSC that I'll talk about a little bit later. Any thoughts before I move to the next slide? Cool. Then I'm going to go forward. So talking a little bit more about tempered binding in practice, here's an example of the Barnase bar star system, which is one of the workhorses of protein-protein interaction investigations. Barnase is in blue, bar star is in green. And this starts off by showing conventional MD run with them starting far apart and letting them come together. And you see they sort of bounce around for a little bit, and then they end up in a conformation they spend quite a long time in. You can see the microseconds in the top left. And if you compare this to the crystal state, you'll see this actually is rotated pretty far from the correct crystal binding pose. So this isn't really where you would hope things would end up if you're looking for the lowest free energy binding state. If we then run with tempered binding, it tries a bunch of different orientations relative to its partner. And then if we look at how this one compares to the state from the crystal structure, it is a very good match. Actual chemists will tell you that particularly some of these side chain interactions that are particularly important, it's nice that those show up in exactly the way that they should. And yes, you see it sort of come into the right low energy state here. And that's probably because it's vastly more likely than the other ones. But in a proper tempered binding run, you will see it explore some of the other possible binding poses as well, if there's any other decent ones. So the forms of enhanced sampling that are available on Anton 2 at PSC are simulated tempering, which I talked about initially. For instance, temperature tempering with adaptive weighting. It doesn't have to be temperature tempering. You can temper various other things as well. There is tempered binding. Then you can set up restraints between the centers of mass of groups of atoms and set them to be a target distance away from each other with some spring constant, saying, we want the ligand and the binding pocket to be either, 0 distance away from each other, or you can set it to further if you want it to be pushed out. And you can also set up conformational restraints based on the RMSD between a atom selection and a target structure. And you could use this, for instance, if you wanted to, say, have some match a protein loop conformation, or temper things in and out of a given conformation of a protein loop. And for the restraints in points 3 and 4 above, the equilibria, the target distances, and the spring constants can be varied during a simulation. You can either do this programmatically, like let's say we want to pull something out over time, or you can have them be adaptively controlled by TSS, which lets you do a form of umbrella sampling. You might say, what is the free energy of being a particular distance away between a group of atoms, or something along those lines. So that's a way to get umbrella sampling in the context of TSS. And there are tools available at PSC to help you set up TSS runs and also to analyze them after you've done them. The link at the bottom here is a link to the PSC wiki describing these tools. And I'm going to talk you through an example of one of those visualization tools for looking at an enhanced sampling run. So a lot of enhanced sampling methods have metrics you can look at that give you some sense of whether they are well converged or not. For TSS, there's a few things you can look at. The top left plot here is a histogram of the visits to the different Hamiltonians, which we call rungs. The red trace is an estimate of what TSS thinks the histogram should look like if you were, asymptotically infinitely long converged. And if this is pretty decent here, it can be a little noisy, that's fine. But if it looks very different, like if all of your histogram mass were on the left-hand side, that wouldn't be a good thing. It would not be well converged. The right-hand side here is a scatter plot over time of the rung visit pattern. You want this to look fairly evenly scatter plotty. There will be parts of it that may be more massive. If you look closely, you can see that it kind of doesn't like to go down to the low rungs as much. But that's not necessarily a bad thing as long as it does it in a fairly even amount of the time. But if this looks really skewed, you probably aren't well converged, and you either need to run longer or figure something else out about your simulation. The plot in the bottom left is the free energy trace. And this may be the observable that you're looking for in some cases. It's if you wanted to see, if you're doing umbrella sampling and you want to know over whatever your reaction coordinate is, what the free energy looks like. This is where you will see it. And you can also get it as a more directly processable output that's described on the wiki page. On the bottom right is a a trace over time of the free energy difference between the first and last Hamiltonians in your simulation, along with a TSS generated online estimate of the error. And in a well-converged simulation, this should look reasonably flat. It shouldn't be jumping around a lot when you get to the right-hand side. And there should be a believable relationship between the estimate for the error and the actual variance in the DG estimate. And as long as that's the case, you can be reasonably confident that your simulation is well converged. If it's not, again, you may need to run longer or do something else. So this is pretty much all of the content I have to talk about. I'm going to put up the survey here. Oops. Michael, if there's any stuff you wanted to jump in with, please go ahead. And if there's any questions, we're very happy to take those.
Yeah, I just point out, so we focused a little bit on the tempered binding, but you can really, by using the things like the RMSD restraints, the distance restraints, you can do a lot of forms of umbrella sampling that people would typically do in other packages. And now with Anton, you'll be able to do it by basically making more umbrellas by having more Hamiltonians. So it's really helpful if you want to really well sample something that you would normally use umbrella sampling for. You can get essentially the same result, but you'll be able to run a denser set of umbrellas, and you won't have to worry too much about how much work you put into each one. It'll figure it out for you. So that is definitely a good use case. And so even though we focused on tempered binding, I keep that in mind when you're thinking about what you might want to do on the machine.
Yeah, thank you. That's an excellent point. I see there's a question about how to decide the relative number of rungs and window size, and whether there's an example of TSS using RMSD restraint. Not enough examples of TSS on the wiki. I'm not super familiar with what's on there. Relative number of rungs and window size, that's a little bit, you sort of have to give it a try, but if you, in general, I would use a larger number, err on the side of slightly larger number of rungs. I wouldn't go higher than a few hundred, but TSS should generally not penalize you for using relatively larger numbers of rungs. The thing that can sometimes slow you down is using too large a window size. So I would try to keep your window sizes not higher than, say, 20 or so. 20 to 40 is probably reasonable. If you go a chunk higher than that, you start to slow yourself down a bit. Not too much, but you may notice it.
So what do you start with? You start with 100 rungs and window size 10?
100 rungs, window size 10 or 20 would be pretty reasonable as just a first guess.
I just have to react to Michael there saying you can add more restraints because there's a limit to how many restraints you can add. This is the tension between the developers and the chemists, and Michael's a chemist. It's like, dude, you've been filing tickets with way too many constraints, with way too many restraints in there. My ideal number is 1. What's your ideal number?
Well, with the RMSD restraints, if you're going to do umbrellas with that, it's really just one restraint where you'll change, for example, the equilibrium point that you want, what you want the RMSD to be. So it's not that bad. That's a pretty standard use. But yeah, definitely don't try to put a whole bunch of restraints simultaneously and change all of them. That's probably a bad idea. And while you can also use these restraints, obviously, just with a regular so-called vanilla MD simulation, right? If you just want to run a simulation with a restraint, you can do that, but that's where you'll start to hit what Ken's talking about. If you try to restrain too many things at once, say like all C alpha distances, you'll start to hit some performance problems. And if you go really high, you'll make Anton really, really unhappy. So I would
it's like
avoid
order
that.
the number of fingers that you have. 1, maybe 2.
Yeah, definitely don't go too far into the hundreds. That's a bad day, and that's when Ken yells at me. Yeah.
Michael.
Let's see.
There's a question about tempering with membranes. So I have not used temperature tempering on membrane proteins, but you should be able to, if you want to do things like temper the RMSD of a membrane protein, an RMSD restraint, that should be okay. I mean, if you tried to bring it to, say, a conformation that would not really be good for the membrane. You might have some issues more with your barostat and maintaining the right pressure, but conformational changes, small conformational changes in a protein, say on the order of like conformational changes that happen in GPCRs or transporters, that should be reasonable. And I think that was the example you're asking about, is the RMSD based method for elevator transporter mechanisms, something like in GLTPH or the excitatory amino acid transporters. That is a pretty big change. So I think you should, you need to test to make sure that the barostat behaves okay. Because if you pull on the RMSD for a big motion too fast while it's embedded in a membrane, I can imagine you would run into some issues with the barostat and maintaining a nice orderly membrane. But just because we haven't tried it doesn't mean it doesn't work. I would just say be very cautious for really large conformational changes.
Can I ask question using audio?
There's hands up. I guess, Marcella, is that cool? Can we do it that way?
Of course, why not?
Yes, sure.
Is it okay? This is a ring asking, yeah, because my question, but I think it's easier just to use audio. So let's say I want to do tempered binding and I want to do charge splitting. There are several ways to do it, right? I can charge split between two proteins, or I can split between one protein and the second protein, but also between protein water, protein membrane, right? So the question is, if I do that way, basically I charge split my protein with all the rest of system. So that's a lot of atom included in the group A and group B. So that significantly reduce the speed.
That would definitely significantly reduce the speed. So if the states you temper to are too non-physical, it's hard to predict, how well your system will recover in that Hamiltonian. So having a protein that's not interacting properly with all of the other atoms in the system could be bad for like the protein's own folding, right? If you unbalance the water protein interactions, you might end up getting the protein to unfold. So I think a general approach is to be conservative about how much you're changing about the Hamiltonian, so that things don't get, irreversibly messed up.
Because the reason I'm asking, because I read Aberpan's paper. In his paper for the membrane protein system, he did mention that he tempered between protein water and protein membrane. So it sounds like it's tempering between protein and the whole rest of system.
Yeah, you can do it. It's the kind of thing where how much you temper, how much you change the interactions is something you have to be careful about to make sure for your application you don't get the non-physical states. It can be good to do like a small pilot run to just make sure that that's not going to happen before you set it to go for whatever your allocation is. Because
Sure.
yeah,
So it does scale. It does scale with the number of atom in
yes,
charge splitting. Okay.
yeah.
Thank you.
I don't think it should slow things down too much. You do have to worry about stability issues.
Oh, okay. Oh, it doesn't slow down, but yeah, stability for
think so.
sure. Yeah, but the speed does not, because they only temper when the atoms are close by, right? Nearby non-bonded electrostatics. So it shouldn't slow down that much with number of atom in the group, I think.
Yeah, I don't think it should
I don't
slow
know.
down.
I don't know. You're the developer.
Yeah, I don't think it should slow down too much, at least. Or at least that the slowdown shouldn't depend on the number of atoms necessarily in
Okay.
the selection.
Okay, thank
Ken
you.
might know more.
I don't know the answer to this.
I don't think it should.
So there are two more questions in the chat. Using words I
yeah.
don't understand.
Yeah, for IDPs, you could definitely do something for IDPs. For IDPs, you have, distances and RMSDs available to you. So you can definitely do tempering from that. And I'm pretty sure people have done temperature tempering with that as well. I don't know, Avi, if you know, do we have a paper out on that already? We
I don't know if
might.
that got
One of Paul
published.
Robustelli's and Albert's papers.
Yeah. Let me see.
Yeah, I'm also looking.
I know they were working on that. I vaguely feel like it did.
Yeah,
No, I don't-
but it's definitely possible. So with that, you probably don't have to worry too much about getting into non-physical states. It'll probably just get disordered and then go back. So yeah, that should be fine to do with an IDP.
Yep. Yeah, I don't think they published it, but it's something that's been tried at least somewhat. RMC restraints in terms of the effect on simulation speed. Ken, what do you think?
Yeah, I'm supposed to know this and I totally don't. Is there like word on the street for how big of an RMSD restraint is reasonable?
I mean, I've
Hundreds?
certainly done ones that do like 10s or 20s of amino acids and not had too much trouble.
Yeah, I've never had, even on proteins with like, if I'm doing C alpha RMSDs, even with proteins like 500 to 1,000, I've never had trouble.
So never had
sometimes-
trouble means like 20% slowdown at most, right?
Like yeah, something I've never noticed the slowdown to affect my work. I do think there's some components where the restraints, and Ken, you'll know how this works better than I do, if they take up too much of the box. So if atoms span like the entirety of your system, there can be problems with Anton with that. That is not my area of expertise, but I've definitely messed up something that way. So I don't try to do RMSD restraints on the head groups of all the lipids in the membrane. I know that doesn't work because I tried. But
yeah, this you want the span of the object to be clearly less than half the box. Otherwise, it's undecidable which periodic image it belongs to.
Yeah, so don't do that. But otherwise, I've never had a trouble with a protein as long as it's solvated enough. I've been able to do all C alphas on any protein I've tried so far.
Cool.
And I have a question, if it's okay. So what would be the best way to get some practical guide? Because this simulating tempering, that's just exactly what I need to do like right now. I need to like accelerate conformational transition. So I'm totally excited. So how I'm opening Wiki, this enhanced sampling pages actually don't open. There is nothing there, but maybe I'm opening something. But anyway, I just want to like go ahead and set up an amp and run. Is there like something like maybe like simple script or like simple guidance side by side? I want to do just this very simple thing to do simulated tempering to like get like, I assume that I'm setting up the temperature and number of, so what are the parameters here when I'm doing simulated tempering? I assume I am setting up temperature increase, right? And I guess like the interval for how long I raise the temperature, or what would be the parameters here?
So if you're doing like TSS style simulated tempering where you don't actually have to set the schedule, it just does it for you.
Okay.
In the temperature section under the enhanced sampling documentation, it gives an example of how you would do it, where basically there is, you said you can't load the page right now, or you can?
Well, I tried to open Wiki and I looked at other resources, enhanced sampling and enhanced sampling update. And it just tells me not found. So this
Yeah, you need to go to DESRES documentation on the wiki.
Oh, okay. Which one?
The DESRES documentation, it says. And then in there, it will be an unsampling.
Okay, I guess if you like send the slides or the link or something, I guess I'll just do it later. But so basically you're saying that over there, I will just find a specific example of where is it done, in ARC file or where these parameters are set up?
ARC file.
ARC file, yeah. So
Yeah,
there would be like an example, okay.
Okay, I'll send you the link.
Thank you so
Ken
much.
just posted it in the chat.
Okay, I will.
Yeah, it's what Ken just posted in the chat, so it's the bottom of the slide.
Yeah, I am. So for those that you don't have an account at the PSC, the wiki is actually password protected. So if you have an account, like you can access.
That part of it is strangely not password protected.
Yeah, I was able to get to it. I don't have an
Yeah, I
account.
was about to say that I also was able to get to it. So that one is definitely open.
And you are okay with that?
Okay, well, I'll figure it out.
So there are a couple other questions. You Lao on group NB type 1. I know who you are now. I've seen this DMS file. It's messed up. We will talk to you by email.
This is to Yun Liu, the person that is having the NB fix problem.
Yes. Yeah, we're looking at that.
Yeah. Okay. Yeah, we are working on that. I sent that to you.
And then Vanessa asks, do these methods work for protein-protein interaction in a membrane protein? Does it select the correct interface, the lowest minimum? I don't know what this means.
Yeah, so I don't know that anyone at Desres has done that much of two proteins in a membrane checking. I assume you're thinking of something like you want to explore different interfaces and find the lowest energy interface. I'm not sure that anyone has done that at Desres yet. It doesn't seem like it would be a problem. I think the bigger problem would be the time for the proteins to diffuse in the membrane. And I know that people who have done this, like with GPCR hormone heterodimers, have had to use enhanced sampling also on relative orientation to speed that up. You could probably figure out a way to do that with distance restraints, but I don't think we've done anything that we can really recommend.
And not to my knowledge. Are there any other questions at the present time? Let's see a hand raised, I think.
I wanted to mention something. I think there was something wrong with the link I sent in the email. Let me put the link, the short link and the long link to the surveys here in the chat. I don't know what was wrong. When I shortened the link, so it didn't work for some people. So I used the long link, but now I read it. I reproduced the short link and it seems that it works. So I'm gonna send you 2 links for the 2 surveys. I will also send everyone an email with those 2 links. Please just fill that forms for us, and it helps us to give a better idea about our how we did these webinars to improve ourselves. Thank you very much.
Thank you, Rosita. And then Christina has her hand up.
Yeah, hi, thanks. You kind of already answered part of my questions, but I'm gonna, again, give a little bit more background of what I want to do. So I have a transporter. I want to sample different states of this transporter along the conformation cycle. The simulated tempering sounds like a really cool way to do that, but because my system needs to be embedded in the membrane, I also have to worry about what's going on with the membrane. And on the example that you posted for simulated tempering, I saw that the temperature changes quite a lot, like from 273 to 400 Kelvin, which will most likely lead to weird phase changes in the lipids. Do you have any experience with that? Any advice that you can give? Maybe for the systems where I suggest simulated tempering, I can just use a very simple membrane instead of the more complex membrane I had in mind, because I wanted to also check some protein lipid stuff. This is the kind of things that I'm kind of wondering right now.
Yeah, I think the RMSD-based method might be a little bit more appropriate when it's in the membrane. I agree that if you do it in the membrane, you should probably do a narrow temperature range, which might not be enough to accelerate the events that you want to see. The membrane is already tricky enough, so I think that if you really want to try with temperature, do a small range of maybe 30 to 40 degrees and make sure that looks good first. But the RMSD one, which you had asked about before too, I think that should alleviate a lot of the problems you might have with the membrane going into the wrong phase, or even I don't know if your mem rates are asymmetric. I imagine at high temperature, you'll get like lots of scrambling issues and stuff like that. So I would probably say that if it was me, I would start with the RMSD, and then if you really want to explore the temperature, you do it a little bit more conservatively. Because definitely at the temperatures that we do proteins, the membrane will not be happy.
Yeah, thanks. For the RMSD, I know we probably are limited by the number of C-alpha, RMSD stuff. We cannot do groups of atoms like centers of masses and things like that with this method, at least to my understanding.
Avi, do you know, is the distances that are implemented, they can do group distances, right?
Yeah, we can. It's just different from the RMSD. That's let's see, that would be 0.3 here.
Yeah, so if you do distances between groups, it calculates their centers of mass and does the distance that way. So if you're thinking about these elevator motions and you want to change the distance, maybe like triangulate something so that you can think about where a domain is relative to the rest of the protein, you could probably do it with the center of mass groups.
Yeah, it's totally fine.
Okay, yeah, thanks. So I can just define several centers of masses and follow them. Do we, for these particular things, are we limited again by how many of these groups we have? We only have 2 groups at all times, right?
Ken, what do you, are there limits there in terms of how many groups they could do in terms of center of mass distance restraints, group restraints?
I'm sorry, I missed the question. So each distance restraint operates on a pair of groups, but you can have more than one distance restraint.
But how many is before things are unhappy?
Yeah.
Oh, you're asking me? I'm a pessimist, so like 2.
I think people have definitely done more than 2, but I don't know how often people have done order, greater than 10.
Yeah, I imagine also analysis might be quite a lot of fun if you want to look at free energies and you have like 4 different variables and stuff. That's gonna be epic.
Yeah.
All I know is chemists can waste unlimited amounts of time screwing with group restraints or restraints of any kind because you're like turned loose to just invent stuff.
Yeah.
Are you saying I waste Anton time, Ken?
Me? I'm not. Am I looking at you? Can you really tell?
Actually, Christina, we had some experience on multiple groups, and I think you have to be careful because the TSS is really just accelerating on one-dimensional collective variable. So if you put multiple group restraints, TSS will consider as just one big group. That's my experience. But if developer can correct me if I'm wrong.
Yeah, that's so TSS is doing one reaction coordinate. Certainly, you can have you'll be moving them all together in a sense.
Yes.
You could have some of them that are just restraints that aren't being tempered, of course, but yeah, they're not moving separately.
Yeah, thank you.
Cool. Sounds like we're winding down.
Thank you very much.
Thank you for having us.
Thank you very much. So
Are
I
there
will stop recording then.